So this is a reference, online translation. So put this reference in the chat. Okay. So I guess it's time to start. And today we have a talk of Sebastian Stich. By the way, what is the proper pronunciation? Stich or Stich?
Yes, the first one, Stich.
Stich, okay, sorry.
It's closer, yeah.
Sebastian Stich from first position was EPF, but now I guess you move to what is the proper pronunciation? CISPA.
CISPA.
CISPA, okay. Please start.
Okay, thank you, Alexander, for this introduction. Yeah, as you mentioned, I'm in the process of moving from EPFL to CISPA in Saarbrücken. And yeah, if you want to, I don't know, visit or collaborate, or just let me know. Okay, so today I will talk about decentralized optimization on heterogeneous data. And okay, the talk is aimed a bit as a bit of a mix of proofs for experts, but also just a general explanation for everybody to follow. What are we doing? So, okay, the first intro is very broad. So what we want to do in machine learning is we want to learn a function from data. So, for instance, we want to make prediction about the weather. So we collect a lot of data of how the world looks like. And then we try to learn a statistical model that makes these predictions. And I mean, of course, there have been many very successful applications of this pipeline in the past. For instance, in classification, self-driving cars, playing games, or in medicine. And one application I really like is all these translation services that exist, and the quality really improved a lot in the last years with all these new models that have been developed. But okay, it's not the purpose of this talk to explain exactly how this is working. We are more interested in how could we learn such a model over data that is stored in a decentralized fashion. So we don't want to aggregate all the data on a single device, but I want to keep the data on the devices where it is stored or generated. So one application you might have heard of is if you have a mobile phone and you start typing some words, the keyboard often starts predicting what could be the next word you want to type or what could be a good fit. So this model combines somehow knowledge from all the users, but it also adds a personalized predictions, just the words that you prefer. And the way this model is trained works basically as follows, that the private data stays on every device, and each device is doing some local training on the data to improve the local model. And then all these devices exchange information, and typically this is implemented with a parameter server that just talks to these devices and aggregates the updates and sends out new and improved models to the devices. And yeah, this is I don't know, popularized under the banner of federated learning, because these devices learn in a federation. Let's make a step and go a bit closer to the optimization task. So we could write this problem of learning something from data I could formulate this as I want to minimize optimization problem of this form. So as I assume that I can decompose the objective function into n components, where here n is the number of devices, and each device stores a share of the function. So for machine learning, this could be like very often the loss function is exactly the same on every device, but just the data is very different. So every device has different images, different type of data. But as we are here in the optimization seminar, we don't really talk a lot about data and so on. We can just encompass all these properties in this notation, where I say every client has a component fi, and we can basically access stochastic sample of this function. So for instance, by looking at some examples in my data, I can get an estimate of this function. And the task is that these clients all together want to minimize this objective, and we want to look at algorithms that are efficient in number of computations and also in number of communications that they need. And of course, if you go to practice, there are a lot more aspects that are very relevant, and not only how can we optimize. But in this talk, I'm mostly focusing on the optimization aspect. So let's say if we would have to come up with one baseline algorithm, what could we do? Well, we all know gradient descent or stochastic gradient descent. And we could just implement this gradient descent. So how does it work? When I'm given a function in stochastic form, I want to minimize this function. And my basic assumption is that I can get one uniform sample of the data. So, and then I could compute the gradient of my function on this data sample. So in other words, I require that I get an unbiased estimator of the gradient of the function. And I think this, okay, in many situations, we can implement such an oracle. For instance, if I have a finite data set, I can just uniform sample a subset and compute the gradient of the loss function on this subset. But if I've not given all the data, so in an online setting, then it's maybe a bit, not so clear if it can really generate uniform samples. So we should just keep that in mind when really implementing this in a practical system. And of course, maybe you don't want to use a SGD. You want maybe to use SGD with momentum or Adam or whatever your favorite algorithm is. But in this talk, I'm mostly focusing on SGD. So before doing anything complicated, let's just recap. What do we know about the convergence of stochastic gradient descent? And in order to formalize these convergence results, we typically need to make some assumptions. And let's say two standard assumptions are that we assume that the variance of these stochastic gradients is bounded by a parameter sigma. And we often assume that the loss function, the gradient of the loss function is not changing too quickly. So when I slightly change the parameter of my model, the gradients are not changing too much. So this is called smoothness. And of course, there are other assumptions that people consider, but these are somehow the most, the most typical ones. And under these two assumptions, we can, for instance, prove that SGD converges to a stationary point. So where the gradient norm is small, in this number of gradient computations. So here epsilon is the parameter that controls the accuracy to which I want to solve the problem. But I mean, somehow the exact formula is not so important for this talk, just that we get convergence results of this type. And of course, if I add stronger assumptions, I can, for instance, prove convergence in different criterions and also can improve the complexity estimates. So what should we keep in mind? That often these theoretical results, they're not exactly what people do in practice. So these theoretical results are proven for a specific output of the algorithm. And this is typically not the last iterate that the algorithm computes. And in practice, we often use just the last iterate. It also requires that the step size is tuned. So depending on the accuracy epsilon, we have to plug in the correct step size to get convergence estimate of this form. And in practice, you would maybe tune your step size depending on the resources or the problem you have. And I think the most critical is that maybe all these assumptions might not hold in practice. So if we don't have a guarantee that our function is smooth, then yeah, these guarantees are a bit meaningless. So they're just like a guideline or an possible explanation what could happen. So, okay, let's, with all this knowledge about SGD, we can now design a first algorithm that could solve this distributed optimization problem. And what we could do, we could just implement something called minibatch SGD, where I compute a stochastic gradient on every device and then just aggregate all these updates on a central server. By this, I have the guarantee that I get an unbiased estimate of the gradient. So my algorithm will converge. And typically I can prove that I even get a linear speed up. So if the stochastic noise is dominating, is very large, by averaging these gradients over n workers, I can accelerate, I reduce the number of iterations by a factor of n. Of course, if the stochastic noise is low, I basically cannot gain anything by this parallelization because I could just solve the problem on one machine, and yeah, this could also work. Okay, so we don't want to implement or look at minibatch SGD in this talk. So why? Well, this training procedure that I've just described would require huge amount of communication. So I have to send the current model parameters from the server to the clients. The clients compute the stochastic gradient and have to send this gradient back to the server. So this is I don't know, requires, and I have to do this with all workers in the system. So this generates a sort of a bottleneck at the central server. And even if I implement this maybe more efficiently with like an all reduce operation, this still requires a lot of communication. So what I want to look at, want to look at algorithms that require only very sparse communication between all these devices. So if here every symbol represents one client in the system, then I want to look at algorithms where in every round of communication, maybe just this guy only talks to maybe 2 of his neighbors, but not to all other devices in the system. So by this, I can reduce a lot the communication that is required. Moreover, we would also like to look at the algorithms that do not require very often to communicate. So maybe I can just skip a few rounds of communication and maybe this still works. And the other line of work is looking at compressing these large messages. But this I will not touch at all, but you can just think of all these algorithms that I present. Maybe you can gain something in addition if you compress the messages or the gradients that you send. Okay, so this was just the introduction and a bit the motivation. And next I will go into like two parts. First, I will talk about just how can we analyze such a decentralized SGD on arbitrary networks. And in the second part, I will I will talk a bit about okay, in the first part we will discover that this basic algorithm that we study first has some limitations or does not work well when the data is heterogeneous. So in the second part, we know we'll look at methods that work better when the data is very different on all these clients. Okay, so this is for the first part. And I realized a bit too late that maybe last year, or I think it was last year, Anastasia already gave a talk on some of the results of this paper in this seminar. So if you have attended a year ago, you would know some of these results, but it may be a good refresher in case you have forgotten. So what is the algorithm we study? I look still at my distributed optimization problem. And I want to implement the following algorithm. I have a different model X on every node I. And basically on every node I do just steps of SGD. So this I know. So on every node, I can compute updates, these SGD updates or gradient descent updates. And after every update, I communicate with all the neighbors in the network. And typically what we do is we just average the parameters over the neighbors in the network. So a way to write this algorithm, I could, it's very useful to write this in matrix notation. So I can build a matrix, which I call big and bold X, where I just add for every column of the matrix, one model, I mean the model parameters from every worker. Then it's just an equivalent way of writing what happens, but a bit more compact. And this mixing matrix W basically encodes the network structure. So for instance, I could implement all-to-all communication by just having a weight of 1 over n on for every entry of this matrix. But I could also just say, oh, I just want to average, every node averages with one neighbor. So I could also encode a scheme like this in the matrix. And the only property I need is that this mixing matrix is doubly stochastic. So the row and columns sum up to 1. And the most typical example is really this uniform averaging weights, where it just, let's say we have a regular graph and every node has 5 neighbors, then everybody would just average with all his 5 neighbors. And this kind of algorithm has been studied a lot in the classic optimization or control literature. And I think, yeah, it started in the 80s or even before. So people were looking at these decentralized gradient methods or decentralized SGD methods. So we would now like to prove that this algorithm converges to a minimizer of the objective function or to a stationary point. So maybe to start, let's just analyze or try to understand what happens when the step size gamma is set to 0. So if I set the step size to 0, then the workers do not look at the gradients, but they just average the parameters with the parameters of their neighbors. And basically, intuitively, what we would expect to happen is that when we run this averaging procedure for sufficiently many iterations, that all the workers converge to the same model, so the same value. So exactly, I can write this even in this form. So I would expect that they converge to X bar, where X bar is just the average of all the models that I use for initialization. And we can even prove this. And to prove this, we need basically two observations. So first observation, which I'm not going to prove, is that the average is preserved over the iterations. So when I start with arbitrary values, all the nodes just average their values with the neighbors. The total average in the system does not change. So I think this is very intuitive, but we can also prove this rigorously. Let's say we have this. Then I can also study, when I do one round of averaging, do I move closer to the global average or not? So let's just write down what this is. So xt plus 1 is just xt multiplied by this W matrix, this averaging step. Because the average is preserved, I can write this a bit in a more complicated way. I can write this as a xt minus bar x, and then multiplied by this mixing matrix of this form. And the interesting property is that this matrix has typically a norm which is strictly less than 1, which basically proves that I decrease, when I start with some distance, I decrease this distance after every iteration. And yeah, this is maybe sometimes called spectral gap or related to the spectral gap. If we look at the classical papers where these results are proven, basically all the results boil down to making the following assumption. So all these results work if the mixing matrix preserves the average and ensures that there is a decrease after every step. And we could write this decrease property in the following form. So if I apply my matrix once, I just move closer to the average of all the values. And I can measure this quantity, how fast do I converge, by a parameter p. And if I have a p strictly larger than 0, I can prove that this gives me linear convergence. So the first contribution we made in this paper I was mentioning was that we somehow generalize this classic assumption. And we generalize sort of in 2 dimensions. First, we observe that it's enough to have this decrease property in expectation. So we don't need to have this in every step. It suffices if this holds on average. And the second property is that we basically just need this decrease property after a fixed number of steps. So let's say I have here a parameter tau, which can be any number you like. And it just requires that after tau averaging steps, I get a decrease of this form. So let's discuss this a bit. So of course, when tau is 1, we go back to the setting on the prior slides. And it's basically just a classic assumption in expectation. And by this, we can model really like random network topologies. Or I think a very interesting case is that we can also model the algorithm that does no communication for a certain number of steps in expectation. So with probability p, we do some averaging, we do communicate with the neighbors. But with probability 1 minus p, I just don't draw any links in this graph, so I do not average with probability 1 minus p. And this is very easy to analyze, and I think it's one or two line proof to complete this. The more difficult part is what they call like a derandomization. So when we have a parameter tau larger than 1, we really allow a deterministic sequence of averaging patterns or averaging topologies. And yeah, the main difficulty in the proof is to handle this deterministic sequence. But it also gives us a bit more, I don't know, allows to apply this analysis to a larger class of algorithms. And for instance, what in this federated learning setting, a very popular algorithm is that we allow every worker to do tau updates locally without communication. And then in the tau step, they would average the models all together or send them to the server. And this we can, with this deterministic model, we can cover this algorithm like exactly. But okay, it's not surprising. The convergence results we can prove for the randomized scheme or the deterministic scheme are the same. It's just a bit harder to prove it for the deterministic scheme. So before I show you the result, I will show you a bit what is the proof. So when we want to analyze now this decentralized SGD for these arbitrary mixing matrices, the proof works basically in two steps. So the first step is that we look at the average of all these models or all these iterates. So this is like something that does not really exist, because I said we don't want to average in every step. So, but in the proof, I can just look at the average of all these models. And basically, we can prove that this average can give us a similar, I don't know, progress guarantees than what we would get when implementing minibatch SGD, except that there is one additional error term, and which we call the consensus error. So if all the models would be exactly identical, then they would be equal to X bar, and the algorithm would be equal to minibatch SGD. So this is what we recover. But if the different models are very different, then we get an additional error term that slows down the optimization process. So in the second step, we need to come up with an upper bound on this consensus error. And for this, we need this assumption on this mixing matrix. And I don't show exactly how this works, because we'll come back to this in the second part of the talk. But we can get the upper bound roughly of the following form. So there's the step size square. This makes sense because the updates are just gradient steps with a step size gamma. There is some parameters that depend on the property of our mixing matrix. And there is some new parameter that measures the dissimilarity of the functions. One way to define it is that we could say, let X star be a stationary point of my function. Then I could look at what is the average gradient norm at this stationary point. And note, this is not zero in general. It could be anything. So is this I don't know, proof sketch? We could now work out all the details, and we get basically convergence results of the following form. So maybe what's easier to describe, I just will go over one line in this table. Let's say for strongly convex functions, the convergence rate consists of 3 terms. So the first term is a sigma square divided by n and mu epsilon. And this is the same term that we get for for minibatch SGD. So if this stochastic term dominates, we get a linear speed up in n, the number of workers, and basically all the other terms do not matter. So this is sometimes advertised as the algorithm is independent of the network topology, and it's independent of the number of local steps or anything. But this only holds in the limit when epsilon is very, very small. So in practice, also these other terms typically matter. And the last term, this is like a pure optimization term. So even if we could have perfect communication, because we do gradient descent, we can prove that gradient descent can never be faster than this number of iterations. So this is not a surprising term, it just has to be there. And then there is a weird term in the middle, but we observe that these terms depend on this dissimilarity parameter. So it's basically saying if the functions are all identical, then the problem is easy. And if the functions are very different, the problem is hard. And actually, it has been proven in work not by us, but by Blake Woodworth and all, that this dependency on this dissimilarity parameter is essentially optimal. So we cannot hope to remove this. Exactly. So I already mentioned this. What I forgot to say is that all these results just depend on the ratio of tau divided by p. So we can basically use tau or p interchangeably. So it does not really matter if you use this randomized or this deterministic mixing property, but they just behave as expected. So I think this is a good result. But it shows that this when we don't have exact averaging, we are typically slower than minibatch SGD that would have exact averaging. So let's just have a brief look at some numerical results. Is this really the case in practice? So what I show here is like just a toy problem for a better demonstration. So we take 25 nodes. I take a quadratic function on every node. And somehow I set up this problem very carefully in such a way that I control this parameter zeta. So I can make all the functions identical, then zeta is 0. Or I can make the functions very different by choosing a lot, and then zeta is large. And I also implement the algorithm with different level of stochastic noise. So in the bottom row, I just use a very large stochastic noise. And just what we see by looking at this plot, no matter what I show, all the curves look very similar. So this verifies that when the stochastic noise is very, very large, the topology, which is indicated by color, does not matter. And also the dissimilarity between functions does not matter because the zeta parameter increases here to the right. However, let's say if I go to the setting where there is no stochastic noise, then I see that when I increase my dissimilarity from left to right, the algorithm gets really slowed down a lot. So this is this. Maybe you can look at any color you wish. The yellow one is when I average on a ring, and this is really strongly impacted when I change the dissimilarity. Okay, so this verifies a bit that, okay, our analysis is describing what is going on, but it's also a bit disappointing because we have proven that the algorithm gets slower when the data is different on all these machines. So in the second part, I want now to discuss options. What can we do if we want to be fast, basically? So how can we design algorithms that are also good when the data is heterogeneous? And okay, for this, we should maybe understand a bit why is this first algorithm not so good. So, and the issue is that a stationary point, so a point where the gradient is 0, is not necessarily a fixed point of this decentralized SGD. So if or decentralized gradient descent. So if right here, this is one update of gradient descent. I multiply by my mixing matrix W. So X star times W is still X star. But the gradient vector times W is not necessarily 0. Why? Because all the individual gradients do not need to be 0. So if I have just a sum of two functions, maybe the gradients could be +1 and -1, and the average is 0, but the individual gradients are not 0. So this brings us, oh no, okay. Just to explain how this showed up in the prior result. So this is a bit, I don't know, a bit hand wavy, but it can be made very precise. So let's say we would implement an algorithm that does tau steps without communication and then just average the updates. So even if we have converged to the optimum point X star, if I do no tau steps, every node is roughly doing tau steps of this order of magnitude. So they will not move too far away from their solution, but they will accumulate tau steps of roughly of this size. This is because the function is smooth. So we assumed it does not change too quickly. Now I just estimate what is the norm of this guy. And you see this norm is roughly gamma square, the number of steps square, norm of the gradient of Fi at X star. And so in expectation over all nodes, this gives me exactly this term, this gamma square, tau square, zeta square that I had in the first proof. So this is why we have this. Just because either because we do local steps or because the averaging is not perfect, we just would move away from X star. So now that we understand that this algorithm moves away from X star, we could try to maybe correct for this. So this is what we call a drift correction. And this idea, I think, appeared in many works. I cite a few below. And okay, the main idea is the following. If we would know what this gradient at X star is, we could just compensate. So instead of moving into the negative direction of the gradient, I could just fix it by adding the gradient at X star. So if I'm now at X star, I just have changed the algorithm in such a way that X star is a fixed point again. And this works great if we would know what is this nabla F star. But of course, in practice, we do not know it. So what we try to, the question is a bit, how can we implement this scheme? So what we would like to do is we want to locally update with a gradient step, like the normal update. And then we want to correct a bit for this local drift. So I want to subtract my estimated local gradient. And okay, this is not mandatory, but I could try to also add the average of all the gradients. So if we do this in a correct way, this is still an unbiased estimator of the. Oh yeah, yeah, okay, of the full gradient. So this is a bit tricky. So this similar correction steps, I mean, appear also in other finite sum optimization problems. So for instance, like this classic variance reduction technique for finite sum optimization problems also uses a similar correction step. But now the question is a bit, how can we implement this in a federated or in a decentralized system? And one way, which I'm not talking too much, not going into too many details, is that if we have a parameter server, so if all these devices are connected to a server, we can basically implement this drift correction on the server. So the server can collect gradients of the clients. The server can compute the average of all these gradients, and then basically we can just send out this average to all the workers, and they can implement this update locally. So this is when the number of clients is not too large, we can do this exactly. When the number of clients is very huge, we maybe don't want to ask every client for a gradient. So we could also do this in a stochastic way by just looking at subset of clients. But I think just in a glance, what we can prove when we do this method with this bias correction, we can typically remove the impact on this data dissimilarity parameter. So I get convergence rates that do not depend on this zeta parameter. So this shows, okay, this is a valid approach. This works. What can we do in a decentralized setting? So if we don't have this parameter server that is doing all the work for us. So there have been an algorithm, I don't know, and some popular name is called the gradient tracking. And it's been presented, a few years ago by two groups like Nedick and Lorenzo and all. They gave it different names, but the more popular, I think, is gradient tracking for the same algorithm. And what is happening? All the clients, they have one additional variable. They have a variable y, where they use in this variable y, they somehow try to track this gradient correction. So this is very similar to what we had before. They add and subtract their local gradients and average this estimate with all their neighbors. So if I go back one slide, it's basically saying, instead of moving just in plus my gradient direction, I should also remove the gradient at x star. And this tracking basically estimates this correction step. And it's also easy to observe that if the algorithm converges to a stationary point, then this stationary point is a fixed point, because every node adds and subtracts their local gradient, so they are not moving anymore. So this is not our invention, but I just want to mention that in a very recent paper, we just have improved the analysis of this gradient tracking method. So convergence proofs existed before, but basically what we did is we improved the dependency on this parameter tau to something that we think is optimal. So it was before something like tau square, and we reduce it to a factor of tau. But that's maybe not so important. The more important fact is that also gradient tracking does not depend on the data dissimilarity. So that's a good thing. This seems to work. But then we see that maybe for stochastic problems, there is one additional term appearing. So it's maybe not ideal, and I think this term could be removed maybe by a different kind of update or so. Okay, one more idea. Instead of designing all these complicated algorithms, maybe we could achieve the same in a more simpler way. And this is an idea, I think, that appears a lot in theoretical papers, because it works in theory, but it does not work in practice. So what is the trick? We basically say, oh, it's an issue that this last term is not 0. But if we would repeat the communication many, many times, then of course we could exactly average all the values and we would converge to 0. So we could now just say we run this averaging or this communication for multiple rounds, and we choose this parameter large enough such that the error gets small. And once we perfectly tune the parameters, all the proofs work and there is no issue. And we can also prove that the data heterogeneity is not, I mean, it does not impact the convergence rate. Okay. Why I say, okay, this algorithm is not practical in my opinion, because, okay, this number of rounds, even if it's like 10, it would slow down your algorithm by a factor of 10. And this is a bit out of scope of what would be very useful. Maybe in this time that you save, you can do other things that are equally good. To make this a little bit more practical, I think it also suffices to choose this parameter R somehow data dependent. So we don't need to pick the same R parameter every round. We could tune it depending on the state of the algorithm. And just a bit of a proof of concept that this could also work. We just one experiment. It's training a deep neural network on Cypher 10 on 32 nodes with the ring topology. And on the left, it's just a plot how this consensus distance evolves over time. So it's the average distance between all the models on the nodes. And okay, this increases, then here the learning rate decreases, and so they move a bit closer together, but yeah, that's roughly the pattern that we get. And here on the right, in the very dashed lines or the bottom curve, it's just a convergence of a decentralized SGD without any modification. And then all these other curves, I just increase the number of rounds of communication gradually, such as to decrease this consensus distance by a constant factor. And when I do this, of course, the quality improves, but also the communication increases. So yeah, this is more like it's not that fully, I don't know, it's not a very practical scheme yet, but it's just a demonstration that, okay, maybe something else could also work in practice. But no, okay, what I want to tell is actually something else. And we could look maybe also at different mechanisms to communicate. So far, I just looked at this gossip averaging, where we just have a graph, everybody averages with their neighbors in the graph. So if I write my SGD update, it's okay, I get an update from myself with some weight, maybe 1/5 if I have 5 or 4 neighbors. And I get some contributions just from my direct neighbors in the network. And it's okay. I'm not so good with intuition, but maybe this makes a bit of sense. No, if it's basically saying I get a lot of gradients just from my closest friends, but all my friends that are in China, they don't communicate directly with me. I just will hear what they are saying over many links, basically. So maybe, I mean, they will tell their friend in the US, and their friend will tell it maybe to me at some point. So the information just spreads gradually. Of course, we can prove that eventually it arrives at my point, but this is a bit the issue why we get this drift. So we don't have the information exactly at the same time. So we could now implement, just as an idea, a bit a different scheme. So I just ask all people in the world to send me their opinion or their gradients. And they write this down on the letter and send this letter to me. And of course, this will take some time. So this information will arrive with maybe a large delay. On the first day, I will see information from my closest friends. And the next day, I will see all the updates from the people in Europe and so on. So, okay, this sounds like a bit of a very complicated scheme to implement, but would this even work in theory? And I think the good thing is yes. So even if these gradients arrive with a delay, that's not really an issue. So we can do some sort of sanity check. Let's say we have converged to a stationary point. Does not really matter if I get old gradients, because all these gradients will be the same if everybody is at the same stationary point. So even if I get gradients that are very old, they're all still correct gradients. So I will not move away from a stationary point anymore, even with these delays. So this is a very good thing. And so we can hope to prove that this delayed averaging is also independent of the data dissimilarity. And this is what we did in a recent work, and with a lot of students from EPFL, and they did most of the work, and I'm just presenting the results now. So what is the exact algorithm? It's just exactly the same thing as what I presented on the idea slide. So instead of using this gossip averaging that somehow spreads information a bit slowly, I would like to implement what we call a relay sum. So it's I would just try to update my model even with delayed gradients. So everybody in the network starts sending their gradients towards my direction. And when they arrive at me, even with some delay, I will apply them. And this guarantees that I get no equal contribution from everybody when I do my update. Okay, you might not think, oh, this is impossible to implement because everybody has to send to everybody. So this is very communication intensive. But there are some tricks to make this a bit more practical. For instance, we could say we just want to route messages on a spanning tree in the network. So that's maybe easiest to understand in a picture. So here I've drawn a spanning tree. And basically this routing, if I'm the node in the middle, basically what I have to do is collect the messages from the nodes on the left, the messages from the nodes on the right. I can just add them to my model and then pass them on to the other side. And by this, I just need to track basically the sum of all the messages that keep arriving every iteration. And it's I just need one, or for every neighbor that I have, I need to keep track of one additional variable. So this is on trees. This is very efficient, memory efficient to implement. Of course, these delays now depend on the diameter, on the size of the tree. And as such, averaging schemes, I think, have also been studied before. So I found 2 PhD theses from about 10 years ago, where the students looked at the exact averaging schemes. And this was one of their proposals. So just passing these messages on trees until everybody gets the right message in finite number of updates. But we combine this now with SGD updates, and we hope that this converges to a minima of the function. So about the proof, this is now very complicated, and I will not mention it. But basically what we want to do is we want to map this algorithm to the framework that we know from the first part. So, and you remember, so we should now come up with some mixing matrix that can describe what is happening. But because I get now all this maybe delayed information, this is not so easy to do. So what we do is we create like a virtual graph where for every node I add tau copies. So a tau max is the maximal delay. So for every time step that the information could be delayed, I add 1 copy in this virtual graph. So now I basically construct a huge graph, but on this graph I can write the update in very compact form. So let's delete all these equations again. What we just have to remember is I can write the update more or less in a similar way as I had before. So I average my parameters and I average the gradients. And this, the way we set up this averaging matrix takes care of the delays and everything. Okay, now I want to go back to my framework and just apply the proof from there. But one second issue is that this mixing matrix that we construct here is not doubly stochastic. So we do not have the property that when I just repeat this mixing step many times, that I will converge to the average. However, I mean, people have studied this, and this is, I don't know, you probably all know what happens is that instead, this mixing procedure converges to a non-uniform average. But we can exactly compute what is this what are these weights basically by computing an eigenvector of this W. Okay, maybe you can now prove a lemma of the form that says when I average or multiply once with my W matrix, maybe I converge closer to this non-uniform average. Okay, but this is not possible. So we cannot hope to prove here a less, because sometimes it can also increase. So I could just give you some examples where this can go up or down. However, what we can prove is that when you wait long enough, so we say there exists a parameter m, probably larger than 1, such that it holds that when I average m times, then I can guarantee that I move closer to this non-uniform average. So this is now a bit combination of these 2 ideas that we saw before. No? First, we need many rounds of averaging to guarantee somehow that we decrease. But it's also, the proof is very similar to this derandomized SGD proof, because we basically need to wait for m number of steps until we can apply this decrease property. So this is yeah, you should read up the details in the paper. So more importantly, we can now prove that this relay SGD converges as we would have expected, and it does not, the convergence rate does not depend on the data dissimilarity. Okay, there are other terms that appear that also depend on the network diameter, but I mean, one property, this data dependence, we could remove. So just to conclude, a few numerical results that maybe also hint a bit at the open problems. So let's say, again, go back to my quadratic problem on 32 nodes on a ring topology. And again, I set up the problem in such a way that I can control this zeta parameter. So in blue is again this decentralized SGD from the first part with just gossip averaging. And we see that when I increase the dissimilarity, this gossip averaging is impacted and becomes slower. In yellow, I show the gradient tracking algorithm. And somehow we also see that this, when the dissimilarity is large, gradient tracking seems to be impacted a little bit. But we have proven it should not be impacted. So there is a bit of a gap that maybe the results are not tight, or all these middle terms I omitted, they also play a role in practice. And then there is in red, this relay SGD that, at least for this problem, is really shows perfect behavior when we increase the dissimilarity. And in green, there is another algorithm I've not mentioned. It's called D-square, and this one also works very well on this problem. On the bottom, it's just some scaling behavior when I increase the number of workers. But yeah, it's maybe too much information to process. Just that, okay, in red is relay SGD, which seems to scale much better than, let's say, gradient tracking, which we have in blue. But we also see that also relay SGD is impacted when I increase n the number of workers. So maybe this could be improved as well with maybe new ideas. Here we also compared just different methods, exactly more or less the same as from the previous slide, on a deep learning problem on 16 nodes, where we distribute the data set in a non-uniform way on these 16 nodes. And we see that, okay, in gray is the all-reduce, all-to-all communication baseline. And this relay SGD is really close to this curve, while the other algorithms are a bit stronger impacted. And we also observed this is very interesting. So not all algorithms, let's say if we keep the number of communication constant every round, but we allow the algorithms to choose a topology that they prefer, then it's not that all algorithms prefer the same communication topology. So I don't know, for sometimes the ring was best, or exactly for this relay SGD 3 is best. So this shows a bit, yeah, I think found is interesting that often the theoretical results assume that the topology is somehow fixed, but actually different algorithms are differently impacted by the topology. So to conclude, and I'm maybe slightly over time, apologies for this. So we have seen some very general framework to analyze various kinds of decentralized SGD methods. So in particular, we can support these local steps. I don't know, different gossip schemes like pairwise gossip or whatever. I've give you a bit of overview of these methods that we know that are not affected by data heterogeneity. So like gradient tracking, or these methods with bias correction, and so on. And on the technical side, I think what I mentioned for the proof in the last part, that we now can handle also not doubly stochastic matrices, like just single stochastic mixing matrices. Yeah, I think this can also be added to the framework, but we have not done it yet. So, but I mean, this is, I think, a very positive side. We can handle a lot of different settings. And we also presented this relay sum mechanism as some alternative to gossip averaging. Maybe a bit to, before you ask me questions, some questions for you. So which methods should we now choose when we want to increase the number of nodes to a very large number? So all the results I've shown were for n less than 100. But what can I do when n is 1,000 or 10,000? And I think there, maybe all these methods do not work so well yet. And is there something better that we can do? We have also looked at all these algorithms in this framework. They have this iteration counter, like the index t. And basically implicitly assumed that all these algorithms update at the same time. But can we also implement something that works without a central coordination? Or is this even possible, to which extent? And yeah, maybe a bit combining these two parts. I also think we are very far away. What we want to do maybe is to solve machine learning or deep learning problems in this decentralized fashion. So these problems have a lot of structure that we're currently not using in our worst case complexity analysis. So maybe by just looking a bit closer to what is the precise problem I want to solve, maybe then it's easier to tackle these questions or these directions. Okay, that's it. So thanks for your attention, and yeah, I really like that so many people joined, and thank you for the invitation as well. Thanks.
Thank you, Sebastian. Thank you very much. It was a very nice talk. Please, questions. You can ask your questions. Just unmute yourself and ask by voice.
Okay. Can you hear me?
Yeah. Yes.
Yeah, great. So a couple of questions related to the this delayed strategy. Could you please clarify whether this tau ij constants, are they some predefined hyperparameters of the algorithm? Yeah, this one.
Yes. Yeah. Yes. That's okay. I don't know how important it is, but yes, in this case, it's predefined because we know what the spanning tree is. And if we just, in every time step, we route the message by one link, basically. So we know exactly what is this tau. But we do not, the algorithm does not need to know what tau is. No. When we implement this, we don't need to know what is tau ij. So in some sense, they are predefined because we fixed the graph. But when we implement the algorithm, we just collect the updates from left and right and add them to our model. And we don't need to know which update is delayed by which delay or something like
that. Okay, great. And then the question related to the complexity of. Well, it says that there is a this is the constant c. Is there any? What is the lower bound? I mean, well, it's clear that the lower bound for constant c is 0. Yeah, but is there any tighter lower bound?
Okay, good that you point me to this slide. I think, oh no, the P has to be there.
I mean,
so
yeah,
I don't know.
so
Yes, it's a bit connected. No, I think this, we cannot be better than, where is the result? This. So, okay, if we plug in tau equals 1, I mean, we know we cannot be faster than this with gradient updates. Otherwise, we would maybe need accelerated gradient methods or so. So if you have a gradient method, exactly the best C would be 1.
yes, yeah.
Yes, but yeah, I think this what we could prove is something like maximum delay to the power 3/2, which is definitely not optimal. I think this we should be able to prove tau maybe, but maybe you can even improve it more. Yes.
Right. Also regarding your experiments, did you pick everywhere the largest theoretically predicted step size? For example, in your quadratic experiments?
No. This is all tuned step size from the practice. So we just took for every algorithm, we run it for different step sizes, and then we take the result that is basically fastest. So it's not, we're not sure. I mean, this theoretical step size could be off by at least some constant factors. So we took the practical tune.
Yes, but they are constant within the iteration procedure.
Yes, they're constant, but I mean, if you take a different constant step size, I can basically draw you any figure here that you like. No, I mean, if the proof maybe for d² or relay uses a slightly different constant for the step size, the slope would be drastically different. And
yeah,
I think that's not the perfectly fair comparison. That's just showing that maybe the proof could be improved or so.
Yeah, I meant that for each method you're using the constant step size during the iteration procedure.
Yes.
Such that, so. Yeah. Okay, thanks. I have no more questions. Thanks for the great talk.
Hello. I got a question that I asked via the chat because I'm not sure if my mic is.
Yeah.
Because I think it's.
Yeah. Okay. So I tried to recap. It's a bit long. So if I understand correctly, you say just if you have this distributed problem, maybe the way I do the averaging or the order I do the averaging, I get different results because of maybe floating point errors or.
Yeah, exactly. And I guess it's every time you do something, it comes in a different order because different workers with no.
Yes. So I think we have a very reasonably good understanding that if you do these minimization tasks, okay, I mean, basically you're right. We could end up in a different local minima, but for all the cases I know, this just floating point errors is not really noticeable scale somehow. But I mean, because basically what people do is they would also add even stronger compression on top of this. So to sense these gradients, we don't need a full floating point precision to exchange these gradients. It suffices to compress to maybe 4 bits or even less. So it's not so crucial because I mean the algorithm will correct these errors anyways because we are minimizing this a function. So it's I think it's a bit less critical than for other numerical problems or so. I mean I would say in my issue. It's maybe not the. I think you don't need to worry about this, but maybe I'm wrong and you find a problem, and then I'm happy to discuss more. Yeah.
Yeah, I understand that. Well, during the iterations, it sort of solved itself. I guess it will mostly be visible if you look at the computation time, the differences between launches, but then it's, well, it's beyond the scope of this talk, I guess. And all right, thank you very much, and for the answer and for the talk as well. It was delightful.
Thank you.
Okay, thank you. More questions? By the way, Sebastian is open for collaboration, and one of his PhD student was Anastasia Koloskova, who come from MIPT, and I guess our student has such a possibility to communicate, to work with Sebastian, and as far as I understand, the direction of collaboration was presented. For example, decentralized distributed optimization and different recipes of this direction. Okay, maybe more questions, but I guess Sebastian could answer if you write him. And is it possible to write you on email?
Yes, yeah.
Okay.
Probably, okay. Maybe don't have it here, but you find it on the. Okay, on my website there should be an email. So it's just my name with a dot in between. So okay, yeah, please reach out by mail or.
Okay.
So maybe mention that you saw this talk. Otherwise,
yeah,
it's hard
if you
to
don't
sort.
mind, we also ask you to send your slides and download, upload the slides on the web page of this seminar, if you don't mind.
Yep.
Okay, great. Thank you one more time. Next time we will have a talk of Eduard Gorbunov. This is joint work with Gautier Guidel. I hope it is also it would be also interesting. Thank you one more time. Thank you, Sebastian.
Thank you.
See you next time.
Have
Bye.
a good time. Bye. Thanks.